So the last time we talked, we were discussing power series. And a power series is just turned out to be an infinite polynomial. And so in your summation, you had c sub n, which is a function of n, times x minus some constant to the nth power. So we tried the simplest one, where all the c sub n's were just 1, and a was equal to 0, and we got this function. And we found out that it was a geometric series. 1 plus x squared plus x cubed. And by finding out where geometric series converge, where the absolute value of r is less than 1, and r in this case is x, we could find out that it converged from -1 to 1. So we had some good news and bad news. We had a function that was not a polynomial that was exactly equal to a function that was a polynomial. The bad thing was that it only worked on values of x between -1 and 1. So we were happy, but went on to a different power series. We took a more complicated c sub n, and we put, instead of 0, we put 2 in for a. But it's still a polynomial, and it still turned out to be, when we wrote it out, a geometric series. So again, we could do two things. We could see what it converged to, the first term over 1 minus the r, and it turned out to be 2 over x. So this function, we had a infinite polynomial, a power series that represented it exactly. And it actually ended up converging on 0 to 4 when we used the test for geometric convergence. Then we went to the last one we talked about, which was a little more complicated, again, c sub n, and we went back to a equals 0 and wrote out this power series. 1 plus x squared over 2 factorial, kept going, and this time it was not a geometric series, so we didn't have a formula that could say what it converged to. We didn't know this time what the function was. That's why I'm saying it's question mark of x. And we also could not use the test that we could with geometric series to find out where it converges. But we were able to use the ratio test. We came up with a new method to find out where, in general, power series converge. And this one, when we did the ratio test, we found out that it converged for all real numbers. So if we really did have it equal to a function, it would be a more valuable function, because we would have more values of x that we could plug into it and still get an answer. Of course, we never have time to put an infinite number of things in, but the more terms we put in, the less we leave off, the better the answer is going to be, the more accurate it would be. But before we gave up on it, we just thought we should plug in a couple numbers into this just to see what the function looks like. We plugged in 1, and we got 2.71828. That was almost identical to e. And then when we plugged in 2, we got a number that was within 1/1000th of e squared. So we had this fantasy that maybe this function is really e to the x. Wouldn't that be exciting if we had, for this transcendental function e to the x, we had a polynomial that would 100% represent it. So after I got done with the video, I was excited enough that I went to the calculator and said, well, it worked for 1 and 2, but let me try a number like 8. And I plugged 8 into the calculator, and I got 2,432. And then I said, I wonder if that's really e to the 8. But I tried it, and it was over 500 higher. So I said, no, maybe this really isn't. But then I got to thinking, remember, we haven't used all the terms. We can't use an infinite number of terms. To do these two approximations, we had only gone up to x to the 10th terms. So the first term that I left off, which would be my error, would be x to the 11th over 11 factorial. Now, when I was using 2, that first number that I would be leaving off would be 2 to the 11th over 11 factorial. And I put that on the calculator and found out that it was very, very small. So it made sense that maybe that error would be pretty small and I would get a pretty accurate answer. And I said, what would happen if I put 8 in here? The first term that I'd be leaving off would be 8 to the 11th over 11 factorial. I wonder how big that is. And I put it on the calculator and found out it was 215. So it made sense that probably I didn't use enough terms to approximate whatever this function is, putting 8 into it. So what I did is I went and I said, what if I go up, instead of x to the 10th, what if I add up to x to the 20th? Then what I leave off, the first term I leave off would be x to the 21st over 21 factorial. And I say, how bad would that be? Well, when I put 8 to the 21st over 21 factorial, instead of getting 215, I only got 0.18. So I said, that isn't so bad. So I went back and took up to x to the 20th terms and plugged 8 in and got 2,980.677, where e to the 8th is 2980.957. It's only off by about 0.3. And the first term would have been off by 0.18. So I have renewed interest that this question mark to the x really could be e to the x. We still have no proof. So, anyway, even if that were true, out of all the functions there are in the world, we only have 1, 2, and maybe 3 functions that we can represent with a power series. And I would like to have a lot more. So I said, what if we went to this rather simple power series, x to the n, from n equals 0 to infinity, which is just 1 plus x squared plus x cubed, and it keeps going. What's something I could do to this? Well, this is just a polynomial, so I know how to take derivatives pretty easily of polynomials. So I said, if this function equals this polynomial, then the derivative of this function should equal the derivative of this polynomial. So I went and I said, okay, the quotient rule, low d high minus high d low over low squared. And what I do is have a different function. So maybe if I just take the derivative on this side, what's the derivative of x to the n? It's nx to the n minus 1. If I want to do it in the summation, or if I did it over here, I'd get 0, derivative of x squared, the derivative of x cubed. I have another infinite polynomial. So what have I done? By just taking the derivative of this function and this power series, I've got a new function, 1 over 1 minus x squared, that I can write as a power series. Now, if you wanted to make this even look nicer, I can see at n equals 0 there isn't going to be anything there. I could start at n equals, or I could just start at n equals 1. And if I really wanted to keep it at n equals 0, I could just make this n plus 1 x to the n. And it looks even a little nicer when you just have x to the n. And if you really want to check to make sure that we did it right in both cases, try n equals 0. What do you get? 1 x to 0, 1. Then n is 1, 2x to the first. N is 2, 3x squared. So yes, we have our fourth function that equals a power series, if this really does turn out to be e to the x. And I got it just by taking derivatives. And I got to thinking, maybe I could have gotten this another way. 1 over 1 minus x squared is really just 1 over 1 minus x times 1 over 1 minus x. So maybe I could have gotten it just by multiplying 1 plus x squared times 1 plus x squared plus x cubed. Do I know how to multiply two polynomials together? Well, we FOIL it. This would be like a superfoil because you have an infinite number of terms. So how do you do this? First you multiply everything over here by 1. So you get 1 plus x squared plus x cubed plus x to the fourth. Then you'd multiply everything over here by x. And you get x plus x squared plus x cubed plus x to the fourth. And then you multiply everything by x squared. And you get x squared plus x cubed plus x to the fourth. What do you end up getting when you add them all together? 1 plus 2x plus 3x squared. You get the exact same thing. So, we haven't added a new one, but we do see there's another way that we could get more functions. You are allowed to multiply them together. You are allowed to take derivatives of them. So, this was starting to get really exciting to me, so I said, what else could we do? So I said, we know, starting again with this same series, could I just take 1 over 1 minus x, and just in place of x, we should be able to put anything we want inside a function. So what I'm going to put inside that function is minus x squared. Well, if I do it there, I've got to do it over here. In place of x, I'm going to put in minus x squared. This is not an unusual thing to do. I'm just plugging something into a function. So what do I end up with? A new function, 1 plus x squared. That's not the same thing as this function. And if I want to write this as a power series, I should say that this is negative 1 to the n times x to the 2n. So this is your c sub n, and this is your x to the n. Okay, so I've really got another one. I mean, we're just building these functions up like crazy. And I looked at this and I said, I wonder what I could do to 1 over 1 plus x squared. I bet I could take the antiderivative of it. Well, if I take the antiderivative of this side, I've got to take the antiderivative of this side, and they should be equal to each other. Now, how do I take an antiderivative of a summation? Well, we know with integrals, if you've got a bunch of terms, you can take them one integral at a time. So I could really just bring that integral sign inside here. Well, on this side, what do you get? This is the integral of dx over 1 plus x squared. That's one of them that we know. It's the inverse tangent of x plus c. And on the other side, we've got the summation. And what's the antiderivative? The negative 1 to the n is just a constant, and you get x to the 2n plus 1 divided by 2n plus 1. And I've got another power series. Of course, it's going to have a plus c, but we can combine these general constants over on this side. And if I start writing out a few of these terms, what do I get? Negative 1 to the 0 is 1 over 1 times x to the first. Then when n is 1, it becomes minus, and now you get x cubed over 3. And then you get plus x to the 5th over 5, minus x to the 7th over 7. So that's what that new series looks like. But I don't really want that c there. So I can plug anything I want in for x. So I'm going to plug 0 in for x. And I get the inverse tangent of 0, which is 0 plus c equals 0 minus 0. So I get 0. So c must just turn out to be 0. So we actually do have another interesting function that we have a power series for. And there it is. Now, having done that, what's something that we could do? We could plug 1 into this function. And we get 1 minus a third plus a fifth minus a seventh. And what is the inverse tangent of 1? It's pi over 4. So we could actually approximate, or we can even say pi equals 4 times 1 minus a third plus a fifth minus a seventh. And that's an exact answer for pi. Of course, we don't have time to do them all. But Leibniz, when he discovered this, he said, this is a way I can get an approximation for pi. So we started to do it, and it actually worked out. The only downside is, since we used this formula right up here, to get this new formula, it has basically the same interval of convergence. And 1 is right on that borderline. So this is where it almost doesn't converge. It converges really, really slowly. So when Leibniz did this, he found out it took 700 terms to get up to 3.14. And he didn't have a calculator. Luckily, he had lots of friends. And it actually takes 10,000 terms to get 3.1415. So it's not, without a calculator, this isn't the best way for approximating pi, but with a calculator, doing this for many, many, many terms would not be that hard to do. So it is a way of approximating pi. Okay, so let's try one more problem using power series. This time, though, instead of starting with something, I'm saying, let's see if we can find a power series for this function. Well, we have no way of going from a function to a power series. So I thought maybe I saw that 1 minus x, and I said maybe we can start the same way. 1 over 1 minus x is that. And how do I get the natural log from this? Well, I can try, if I just put a minus sign right here and take the antiderivative, this is going to be a natural log. I've now got it in the form of du over u. Now, if I'm going to put a minus sign there, I have to put a minus sign here, and I have to take the integral of this side, which again, I can bring the integral inside. So this becomes what? The natural log of 1 minus x plus c. And on this side, I get x to the n plus 1 over n plus 1 plus c. But then I can combine the c's together. So if I write this out, I get minus, in the first term when n is 0, is x. And then I have plus x squared over 2 minus plus x cubed over 3. And then I keep going. Then I could put in x equals 0, and I get the natural log of 1, which is 0 plus c, equals minus 0 plus 0 plus 0. Again, c turns out to be 0. And I've done exactly what I was looking for. I found a power series to represent the natural log of the absolute value of 1 minus x. Now, this question said, explain the useful of this to approximate the natural log of 1.1 and the natural log of 2.2. Well, I could use the ratio test to see where this converges, like we were doing yesterday. But again, I started from this geometric power series, which I know converges from -1 to 1. And that's all. So what would I have to do to get the natural log of 1.1? I'd have to plug in to this x equals -0.1. Well, that's within our interval of convergence, so that would be okay. But what would I have to do to get the natural log of 2.1? Then I'd have to plug in -1.1, which is outside our interval of convergence. So it's not going to do a good job at all. So I would not want to use it for this, but I can use it to find the natural log of 1.1. So what am I going to do that? I'm going to plug in -0.1 here, which means I'm going to plug the same thing in over here. And I might as well just do it here. So I get -0.1 plus 0.01 over 2 plus a -0.001 over 3, and then it's going to keep going. So altogether, this becomes 0.095 if I use just the first two terms. And it says to use two terms to approximate that number. So I would have 0.095. And I even can tell how accurate that is because this is an alternating series. And we have that alternating series estimation theorem, which says the error is less than the first term that you omit. Well, the first term I omit is right there, so my error should be less than 0.00033. So this should be an awfully good estimation of the natural log of 1.1. And I looked up the natural log of 1.1, and it was 0.0953. So you can see we were off by just about what the estimation theorem told us we were going to be off. And it said we were going to be off by less than this, and we were. We were off by 0.0003. So the theorem did a good job of estimating. So I guess I'm hoping you're seeing that these power series are going to be very useful, especially the more functions we can come up with, the better. So the next talk we have, I'm going to see if we can come up with even a better way to get more functions that can be represented by power series. Now, just because I have a little extra space here, there's something that showed up that you might have looked at and wondered why, when we had n equals 0 to infinity, and we had x to the n over n factorial, when we plugged in 0, we got 0 factorial. So, does 0 factorial even have a meaning? And it really doesn't. If you have 5 factorial, it means going 5 times 4 times 3 times 2 times 1. You always go down to 1. So 0 factorial really doesn't have a meaning, yet it shows up in this power series. It shows up in calculations. So we have to come up with what it is. Well, it's very similar to the question is, what is 9 to the 0 power? That doesn't have any meaning. 9 squared has a meaning. It means 81. 9 to the 1/2 power means the square root of 9, or 3. 9 to the -2 power means 1 over 9 squared. 9 to the 0 power doesn't have any meaning. But yet, we always say anything to the 0 power is 1. Well, why is that? It's because if you have, say, 9 squared divided by 9 squared, we know the answer is 1. And the rules of exponents say the answer would be 9 to the 2 minus 2. So to make the rules of exponents work, we always define any number to the 0 power to be 1, even though it doesn't have a meaning. Well, this doesn't have a meaning either, but it makes factorial sense. Because what is n plus 1 factorial? It's n plus 1 times n factorial. And what happens if I put 0 in here? I get 1 factorial, which is 1, equals 0 plus 1 times n factorial. Times 0 factorial. So that shows that 0 factorial has to be defined to be 1 to make sense out of the rules of factorials. Just like anything to the 0 power has to be 1 so that it follows the law of exponents in algebra. So I just wanted to throw that in there because we're going to be dealing a little bit with power series where 0 factorial shows up. So, you take care till the next talk.